Hi students, today's topic is time dependent perturbation theory. It is an approximation method in which total Hamiltonian have explicit time dependence. The time dependence will be incorporated in the perturbation. As I have shown, the perturbation V has time dependence. In equation 1, Hamiltonian is H naught is unperturbed Hamiltonian of a system whose eigenstates and eigenenergies are known. Operator V shows any time depending perturbation. For example, it may be interaction of system with any external agencies. We have taken the assumption that the interacting perturbation should be very small than H naught, which is the unperturbed Hamiltonian. The solution of unperturbed states may be stationary states as shown in equation 3. Let consider a system is subjected to small perturbation for a time tau. The Schrodinger equation in time 0 to tau can be written as in equation 4. You know the state in Schrodinger picture, the state vector only evolve with time, but here you can see operator H naught plus V is also depending on time. So this problem will be solved in interaction picture. The main task of this problem is to find probability of system to be found at later time in another perturbed eigenstate psi f from psi I. Psi f is final state, eigenstate of final state, and psi I is the eigenstate of initial system. To deal perturbation in interaction picture, equation 5 shows Schrodinger equation in interaction picture. Equation 6 represent evolution of state vector in interaction picture. Equation 7 is representation of operator in interaction picture. Exponential of minus iota h naught t over h cut is time evolution operator u, while exponential of plus iota h naught t over h cut is inverse of u. Equation 8 shows time evolution of state vector psi t from initial state vector. The initial time is shown with ti u into t comma ti is time evolution operator from initial time ti to final time t. Put 8 in equation 6. Doing some simple steps, we have time evolution of state vector in interaction picture from initial time ti, which is also in interaction picture. Equation 11 again shows the time evolution of state vector in interaction picture from initial state. Now substitute in equation 5, we have first order equation in u. To solve it, we should know the initial condition. Time evolution operator in interaction picture is equal to 1 when both time are same, as at that time initial state vector is equal to final state vector. Integrating equation 11 from limits ti to t, we have equation 13. We will solve it by using iterative method. In iterative method, you make an initial guess and generate sequence of approximation solutions from previous one. First order approximation is obtained by inserting ui in integral sign. Equation 14 is first order approximation. Now put this result in equation 13 to obtain second order approximation. To obtain third order approximation, we will have to put the second order approximation in To obtain third order approximation, we will have to put the second order approximation in again in the integral sign. The solution of any order can be find out by this procedure. In the last, I have written higher order approximation, which is known as Dyson series. It allows to calculate state vector up to desired order. Thank you, dear fellows.